So I'm going to be a little bit painful and move on and do variance and standard deviation as well. I don't really want to do them both in one go, but I don't really have a choice because the exercise goes straight into both of them. So I probably need to teach you both. But I'll only do 2 of these examples, and I'll save one example, which is probably the closest thing I have to a complex unfamiliar, for Friday. So variance and standard deviation. A couple of little conversations going on underneath me at the moment. Cool. So recall that the standard deviation is, and it's been touched on in the past, but again, you may not quite recall this, so I'm going to explain it to you again. The standard deviation measures spread. So if you calculate the standard deviation, which can be done on your calculators, can be done in Excel, and can be done by formula, if you calculate the standard deviation, it measures the average distance each data point is away from the mean. And obviously, if that average distance is larger, then the data is more spread out. So that means it's a measure of spread. It numerically measures the average distance of each data point from the mean, and a small standard deviation means there's more consistency in the data. It's less spread out. A large standard deviation means there's less consistency in the data. Typically, the actual number for standard deviation doesn't mean a lot in context. If you get a standard deviation of 2, that doesn't mean a lot. But if you have 2 data sets and one has a standard deviation of 2 and one has a standard deviation of 5, then that can mean a lot. So for example, if we compared, say, your exam results to Miss Fazani's class exam results, and we had the same mean, but her standard deviation was 2 and ours was 15, well, that would mean that you're performing, we'd probably have the top performer in the group here, but we'd also have the lowest performer. And, there might be something that I can take out of my teaching and look at. Any questions on that? I'm just going to spew out some formulas for you now. The variance is the standard deviation squared. So as you're tracking along determining the standard deviation, you'll hear more about standard deviation than you will variance, but it does come up in this topic. The variance is the standard deviation squared. It's labelled var x, and standard deviation is labelled in the textbook as SDX, but it can also be called sigma, another Greek letter. It's an O that's kind of winking at you, or maybe an O with an eyelash or something. That's sigma. And you've used sigma today already. You've used the capital version, which means sum of. That's that crazy looking thing, the one that looks like a really square 3. This is lowercase sigma. The variance is the standard deviation squared, so therefore down here the standard deviation is the square root of variance, and that connection is going to be important as well. It does mean though, and I can't remember what's on your formula sheet exactly, but it does mean that if you know the standard deviation formulas, well, you know the variance formulas because you just square the standard deviation formulas, or vice versa. Chris? Yes. Yep. That is the little O with an eyelash. There's no symbol I'm aware of for variance, and there's not one used in the textbook. And your variance comes up a bit, but standard deviation comes up a lot more. So here's our calculating. There are 3 formulas. I'll point out the one that you're going to use most commonly. Oh, there's 2 probably that you'll use a lot. So the variance is the average distance from the mean squared, and the standard deviation is just the average distance from the mean. So here's our dual formulas you'll note here. Either the variance is the average distance from the mean, x minus mean, squared, and remember our expected value was the same as our average. So it's the expected value of this data. Now this first one is kind of the one that rolls off the tongue better. It's the one that matches with the definition of variance and standard deviation, but it's not really the one that you'll use. And I'll show you why and where the one you'll use more. It does mean the standard deviation is a square root of the variance, so it's just a square root of that. The second one you'll use a lot, this is the one that you use in the table. So the variance is equal to the distance between the standard deviation and the mean squared multiplied by the probability. And then you sum those up because it's the expected value. So that comes directly from the top line, which is the expected value. And remember, the expected value is always the data point times by the probability of that data point. there's the data point times by the probability of the data point. That's for the variance. You'll note one thing that's there that wasn't referenced in my discussion of the average distance from the mean, and that is if you have the mean here, so there's my mean of a data set, and you've got some data points and they're here, 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 here. If you find the average distance of each of those data points from the mean, so you find this length, this length, this length, this length, and this length, and add them together and divide by 5, what will you get? Any takers? Every single time.
The average?
The average. What should the average distance from the mean be? Just by the definition of what the mean is. Sorry?
0.
0. So this average distance will always be 0. And that's a problem for us because it means we can't measure the average distance. And the problem is that some of them are positive and some of them are negative. So we fix that problem by getting the negative ones and making them positive, which can be done with an absolute value function. But an absolute value function is hard to deal with mathematically. The way to deal with things mathematically like this is we just get each of these values, whatever they are, x minus mu number 1 and x minus mu number 2, and we square them all. And when you square them, the positive ones stay positive and the negative ones become positive. And then you average all the squared values, and that will give you your variance. And then you take a square root, which cancels out the squaring, and that's why the standard deviation is the square root of variance. So the variance and the standard deviation are exactly as you'd expect. They are the average distance from the mean, except early on we square it so that all those average distances become positive. And then at the end we take a square root, and that cancels out the squaring and gives us a standard deviation. So mathematically it works really nicely, but there is that square and then square root factor. The last one which you might use as well is you can also get the expected value of x squared, which will just be x squared times the probability of x occurring, and subtract from that the mean squared. That will also give you the standard deviation. But in all honesty, I will be using the second one almost always, depending on the context, and you'll need to see different examples in the textbook of which one is which, etc. I'm going to do a couple now, just a couple. Example 4 and 5 are just some calculations. One is calculating the variance standard deviation of a dice roll, and one is calculating the variance standard deviation of the sibling data. And I'll show you how we can do that in a table using these formulas, and then we'll go from there. Here we go. Calculate the variance and standard deviation of the outcomes of a dice roll. So let's do this one first, and I'll show you how you would build the table to calculate this. So first of all, x can be 1, 2, 3, 4, or 5, or 6, and the probability that x equals x is 1/6 in all cases. They're all equally likely. So we have that information for a dice roll. Second, though, to calculate the variance standard deviation, we need to first recognise what the mean is. What's the mean of this? 3.5. We calculated that earlier in example 1. Let's go with example 1. So now what I'm going to do is I'm going to model this second formula. So that is that the variance var, I'll do it over here, var x is equal to x minus mu squared times by the probability of x minus equals x. And it's actually equal to expected value. It's actually equal to the sum of that. Why have I not written that down? Wait, I'll backtrack on that in a second. So it's the sum of all those. So I'm going to start by calculating. I've got my x, I know my mu. Let's work out what x minus mu equals. I'll have a new column, and in that column I'll work out x minus mu. 1 minus 3.5 is negative 2.5. 2 minus 3.5 is negative 1.5, negative 0.5. 0.5, 1.5, 2.5. And then I'm going to determine in my next column what x minus mu squared is equal to. And x minus, so I just square these, and hopefully you know that negative 2.5 squared is a positive at 6.25. I've written 2.2. 2.25, 0.25, 0.25, 2.25, and 6.25 is the sum of my x squareds. And then I get that, and I multiply by the probability. So I get x minus mu squared times by the probability that x equals x. And so I've got 1/6 of that. I've got 6.25. I'm going to break things and write it as a fraction for now, because I know that eventually I'm going to add them up. 6, 0.25 over 6, 0.25 over 6, 2.25 over 6, and 6.25 over 6. And then my sum, so my variance of x will be equal to the sum of these values, which will be equal to 6.25 plus 2.25 is 8.5, 9 plus another 8.5 is 17.5 over 6, which can be better written as 35 over 12, or what's that, 2 and 11/12. So my variance is equal to the sum of all these values, which I'm going to have to backtrack and put in that formula. So if I ruin what you've written down, I'm sorry. Yeah, I'm sorry. So there's my variance. And of course, if I want to work out sigma, that's equal to the square root of variance. And in this case, it's equal to something not as nice. There we go, that will do. So I calculate the square root of 35 over 12. And that gives me 1.71 approximately. Now what you should find, typically, particularly with a nice evenly distributed set, you should have 3, 4, 5 standard deviations existing in your range. So we can get a 1 to a 6, and that range is about 3 standard deviations, which is about right. So you can expect that. That's pretty typical. Any questions on that? That's variance and standard deviation. It just follows that table formula, and you can build an understanding out pretty quickly. Let's do the same thing for the sibling data. And with the siblings data, you'll notice that because of the way the data's heaped together, I would expect the standard deviation, the variance, or the range is 5 again, I would expect the standard deviation to be probably a bit smaller, because I'm less likely to get the outliers than I was in the previous set of data, and the range is the same. That 2, the 1, 2, and a bit of 3 dominate the data set. But this data set, this data value down here, will spread my range out a little bit, but not that much. I'm expecting about 1.5. And so I'll go through again. I'll start by writing down my probability that x equals x, and we had these before, 3 over 20, 4 over 20, 10 over 20, 2 over 20, and 1 over 20 here, and 0 over 20 there. And then I'll work out, remember we worked out our average earlier. What was our average earlier? 1.75. 1.75 average. So our x minus mu will be negative 1.75, 0.75, negative 0.75, 0.25, 1.25, 2.25, 3.25, and our x minus mu squared is a bit of a pain. Actually, let's just do this all in one go, because I can work them out. Let's do our table. Stop being lazy. 1.75 squared is 3.0625. 0.75 squared is 0.5625. 0.25 squared is 0.0625. 1.25 squared is 1.5625. I don't really need 2.25 squared because it's got a probability of 0 anyway, but I'll put it down. And then 3.25 squared is 10.5625. And my x minus mu squared times the probability that x equals x is just this column here multiplied by that column there in each case. So it's 3.0625 times 0.15. So this is 0.459375. The next step I'm going to do is to sum these together. So if somebody's sitting around with a calculator right now and wants to save me the time of blundering away, that'd be really helpful. I'll put these on and add them down. 0.2 times 0.5625. This is 0.1125. 0.0625 times by a half is 0.03125. 1.5625 times by 2/20 is 0.15625, and then 10.5625 times by 1/20 is 0.528125, and that's 0. And therefore my variance is equal to the sum of that, which is equal to, I see at least one person helping me out. 1.2875. And so can you do this for me quickly, Reggie, and just do the square root? 1.13468. So actually slightly lower than I expected. I was expecting 1.5, give or take, but still very reasonable. And you notice the effect on the data points have. So whilst 10 of my data points are 2, because they're so close to the mean, the actual effect they have on the standard deviation is 0.03, whereas the effect that one data point at 5 had was 0.52. That one data point drags the standard deviation up quite a bit. This one also has a big effect. Without those two, we'd have a standard deviation of almost nothing. And that's what you expect, because they provide spread, so they widen the standard deviation. So that variance and standard deviation calculation will take a bit longer to do by hand, and you will almost certainly be required to do one by hand next term, so make sure you know how to do it. Here is my last example, which I'm not going to do with you now, but it's a bit of a doozy, as you can see. So I'll leave you, if you want to play with that, you're welcome to, but I suggest you do the exercise first. If I could just go in here really quickly and ruin your formulas, just the middle one, and throw in that sigma, sum of, which means I need to throw in that sigma there. That's not the sigma I want. Then that's going to work better. I might even put an extra bracket around just to make sure that you sum the probability component as well. That's a silly noise to put on the end of my video. Okay, that's it. I'm done.